Welcome back to the next video about the Poisson distribution. This is another discrete probability distribution after the binomial. Let's assume random variable x follows Poisson distribution with parameter lambda. Here lambda is called the parameter of the distribution and lambda is positive. So if x follows Poisson with parameter lambda, then probability function fx, probability capital X equals to x will be lambda to the power x e to the power minus lambda by x factorial. So this is the formula of the probability function of Poisson distribution, and this should be remembered. This is very useful in many problem solving cases. So here x can take value from 0, 1, 2 and up to infinity. This is again the discrete distribution as I have already mentioned, and lambda is always positive. This you have to remember. Now we will look at some properties of Poisson distribution. The first property is the mean. This is very easy to remember. Mean is the parameter itself, which is lambda. Next is variance, and again variance sigma square is also the parameter lambda. So mean and variance are same here. The third property is coefficient of skewness. The formula of this is alpha 3 equals to 1 by root over of lambda. So alpha 3 is positive here. Then coefficient of kurtosis, and this is alpha 4 equals to 3 plus 1 by lambda. The fifth property is the moment generating function. The formula for this is mxt equals to e to the power lambda e to the power t minus 1. And the last property, characteristic function, which can be remembered from the moment generating function itself. This is phi x omega equals to e to the power lambda e to the power I omega minus 1. Just replace I omega in place of t. So moment generating function you will have to remember, and this mean and variance you will have to remember. Next, we will see the relationship between binomial and Poisson distribution. Let random variable x follows binomial distribution with parameters n and p. So if n is large, how large? One thumb rule is it must be greater than or equal to 50. And the second condition, if p, the probability of success, is small, how small? Such that the np, this value, is less than 5. And as p is small, the q is close to 1. So the probability of not occurring the event is 1. So we can say that the event is a rare event. So in this case, when the event is rare, then x can be closely approximated by Poisson distribution. With parameters lambda equals to np. Here the connecting thing is the mean of both the distribution binomial and lambda. For binomial, mean is np, and for Poisson, mean is lambda. So those two will be equal in this limiting case. Next, we will see the relationship between normal distribution and Poisson distribution. Let us assume that random variable x following Poisson with parameter lambda, then x minus lambda by root over of lambda. This is the standardized Poisson. Remember, mean is lambda and standard deviation is root over lambda. This follows normal 0 1 as n tends to infinity. So in this limiting case, the standardized Poisson, which is the left hand side, x minus lambda by root over lambda, this is standardized Poisson distribution, and the right side is the standard normal distribution, normal 0 1. So when n tends to infinity, these two things are equal. Not equal, actually, very close to each other. This can be approximated by the other. Now we come to the most important theorem in all statistics and probability and data as such, which is the central limit theorem. So I hope you have noticed that the binomial distribution and the Poisson distribution, these two discrete distributions are closely approximated to normal, a continuous distribution, when n tends to infinity. So in that limiting case, so the question arises, is it the case with binomial and Poisson only, or is it the case with any other discrete distribution? The central limit theorem gives the answer. So let x1, x2, like that xn are independent and identically distributed. So we call it as IID, independent and identically distribution, IID. So let x1 and xn are IID, random variables, n random variables, each having mean mu and variance sigma square. Then let us define Sn, which is the sum of all these random variables, x1 plus x2 up to xn. So we can say that Sn is sum of n IID random variables. So now note that the mean of Sn is n mu. There are n elements and each having mean mu, so mean is n mu, and similarly variance is n sigma square. Now according to the central limit theorem CLT, Sn minus mu of Sn, that is n mu, divided by the standard deviation, which is sigma root over of n. This follows normal distribution with mu 0 and variance 1, and this happens as n tends to infinity. The number of random variables, number of IID random variables tends to infinity. So you will have to remember this. This is very important. I guess I have made a mistake earlier. Yes, here it is. This is not lambda tends to infinity. This is n tends to infinity. There is a reason why I am saying that the central limit theorem is the most important theorem in all over statistics and in the data realm. Because the central limit theorem, it reveals a hidden order in apparent randomness. So notice that these x1, x2 dot dot up to xn, these random variables, I have said these are identically distributed and they are independent. But the type of distribution is not mentioned here. It can be binomial, it can be Poisson, it can be any other distribution. But as long as they are independent and identically distributed with same mu and same variance, then their sum Sn, the standardized form of that sum, that is also a random variable, and that follows a normal distribution with mean 0 and variance 1. And the more fascinating case is that it can also be shown that this theorem is also true under a more general condition. For example, it holds when all these small random variables x1 to xn, they are independent with same mean and same variance, but they are not necessarily identically distributed. Even in that case also, the central limit theorem holds true. So, to summarize in a nutshell, no matter the original distribution of a population, the average of its samples tends towards the normal distribution as the sample size increases, as n increases. This holds true even for widely non-normal data. This universality simplifies complex statistical analysis in many cases, and it allows us to make powerful inference with just the mean and standard deviation, making it a cornerstone of many statistical reasoning. With that, we will end this video here, and in the next video, we will discuss some problems about the Poisson distribution, which will make you understand this distribution even in a better way, and you will learn to solve some real world problems with this Poisson distribution concept. So, see you in the next video.